August 15, 2024, 2:47 p.m. Eastern Time. 60 data centers in Northern Virginia's data center alley simultaneously disconnect from the electrical grid. Not a planned maintenance. Not a cyber attack. An emergency mass exodus triggered by what federal regulators would later call an unprecedented surge event that nearly cascaded across the Mid-Atlantic region. Within minutes, PJM Interconnection, the grid operator serving 65 million Americans, was scrambling to cut power plant output across 7 states to prevent a blackout that would have made the 2003 Northeast blackout look like a neighborhood outage. The cause? These data centers, housing the AI infrastructure that powers ChatGPT searches and Microsoft Copilot queries, had detected voltage fluctuations and automatically switched to backup generators. All 60. Simultaneously. The grid surge from their sudden departure, equivalent to Boston's entire electricity demand vanishing in 12 minutes. This isn't a story about future risk. This is happening right now. And the financial forensics reveal something far worse than a grid stability problem. They reveal a systematic cost transfer from big tech to American households that has been hidden in plain sight. Here's what Amazon, Microsoft, and Google do and advertise in their earnings calls. AI inference costs 6 to 10 times more electricity than traditional web searches. When you ask ChatGPT to write a short email, you're consuming the equivalent of running a microwave for several minutes. Multiply that by billions of daily queries across hundreds of millions of users. And you begin to understand why data center electricity consumption jumped from 415 terawatt-hours globally in 2024 to a projected 945 TWh by 2030. But the real revelation lies in the cost structure. According to McKinsey analysis obtained through industry sources, the entire compute power value chain requires $5.2 trillion in infrastructure investment by 2030 to meet AI demand alone. Not software development. Not model training improvements. Pure physical infrastructure. Power generation, cooling systems, electrical distribution, network connectivity. Wood Mackenzie's grid analysis tells the deeper story. Data centers tracked in their database will require 334 gigawatts of power capacity by 2030, up from 77 gigawatts in 2023. That's a 334% increase in 7 years. For context, the entire United States currently operates 1,200 gigawatts of total electrical generation capacity. AI infrastructure alone will consume more than 25% of America's current electrical system within 6 years. The problem isn't just scale, it's concentration. 60% of America's hyperscale data centers cluster in 5 regions: Northern Virginia, Atlanta, Phoenix, Silicon Valley, and Chicago. These digital cities now draw electricity loads comparable to major metropolitan areas, but with power density patterns that stress transmission infrastructure in ways urban planners never anticipated. The August incident in Virginia wasn't isolated. It was symptomatic of a systematic infrastructure mismatch between AIS power requirements and America's electrical grid capabilities. Here's the technical reality. Traditional data centers operate at 10 to 15 kilowatts per server rack. AI-optimized hyperscale facilities require 60 to 120 kilowatts per rack, a 6-10x increase in power density that transforms cooling from an operational cost into an engineering crisis. When Microsoft announces a $500 billion Stargate project with OpenAI, they're not just buying GPUs and real estate. They're commissioning electrical infrastructure that rivals small countries. The Stargate build-out alone will require 5 to 7 gigawatts of power capacity, more electricity than Ireland consumes annually. Finding that power means either building new generation capacity or diverting existing supply from other economic activities. Dominion Energy, the utility serving Data Center Alley, provides the clearest example of infrastructure strain. Historically, the company built approximately 2 electrical substations per year. They currently have 50 under construction. Their regulatory filing from March 2024 projects a 15% base rate increase over 2 years specifically to fund transmission upgrades for data center connectivity. For residential customers, this translates to average household electricity bills rising 50% by 2039. The Union of Concerned Scientists calculated $4.3 billion in utility infrastructure costs during 2024 alone to extend transmission lines for data center connections. Individual projects range from $25 million to $100 million per facility, costs that regulatory structures automatically pass to ratepayers through utility rate adjustments. But transmission represents only the visible infrastructure cost. The deeper financial disruption occurs in electricity markets themselves. At PJM Interconnection, capacity auction prices spiked 800% in 2024. These are spot market fluctuations driven by weather or fuel costs. These are structural pricing changes driven by data center developers' willingness to pay any price for guaranteed electrical capacity. Because power represents less than 0.5% of total data center construction costs, developers show complete price inelasticity. They'll pay $100 per megawatt hour or $800 per megawatt hour with equal indifference. The result? Consumers across 7 PJM states paid $4.3 billion more in 2024 to cover data centers' transmission infrastructure. CNBC's analysis of federal data reveals PJM's 65 million consumers will pay $16.6 billion total through 2027 for future power supplies to meet AI data center demand, approximately $255 per person. This isn't free market pricing. It's cost socialization. Data center operators capture 100% of AI computational value while transferring infrastructure costs to residential and commercial ratepayers through regulatory mechanisms designed for gradual, distributed load growth. Regional patterns confirm this cost transfer operates nationwide. In states with the heaviest data center concentrations, residential electricity prices spiked dramatically. Illinois up 20%, Ohio up 12%, Virginia up 9% in September 2024 alone, according to Energy Information Administration data. These aren't seasonal adjustments or fuel cost fluctuations. These are structural rate increases driven by utility infrastructure investments to serve hyperscale AI facilities. California provides the most extreme case study. Pacific Gas and Electric residential rates rose 63% between 2021 and 2024. Southern California Edison rates rose 52%. These are now the highest residential electricity rates in America. While multiple factors contributed, California legislators have identified the correlation between AI infrastructure build-out and residential rate increases as clear and undeniable, according to Assemblymember Rebecca Bauerkahan's legislative testimony. Grid stability represents only one dimension of the infrastructure crisis. The deeper constraint involves cooling technology and water consumption. AI-optimized data centers generate heat loads that require liquid cooling systems, copper cooling plates attached directly to each processor chip. The National Electrical Manufacturers Association estimates cooling accounts for 30% of data center energy consumption, and this percentage increases with AI workload intensity. The cooling requirement creates a cascade of resource demands: copper for cooling plates, water for heat exchange, additional electricity for cooling systems, specialized chemicals for thermal management. A single AI-ready hyperscale facility consumes 2.5 million gallons of water daily for cooling operations. Google's data centers consumed 5.6 billion gallons of water in 2022, before their major AI infrastructure expansion. But water represents just the visible resource constraint. Copper demand for AI data centers will reach 1.1 million tons annually by 2030, according to Wood Mackenzie's materials analysis. Copper for internal facility infrastructure, plus an additional 5 million tons for transmission and distribution infrastructure to connect these facilities to the grid. In a commodity market already facing supply constraints, AI infrastructure is creating inelastic demand that competes directly with renewable energy projects, electric vehicle manufacturing, and traditional construction. The semiconductor industry provides the final bottleneck. TSMC's 2nm process technology, essential for the most advanced AI chips, requires copper interconnects at microscopic scales. As chip architecture advances, copper purity requirements become more stringent. Any disruption in semiconductor-grade copper supply directly impacts AI chip production capacity, creating feedback loops between physical commodities and digital infrastructure. NERC's Director of Reliability Assessment, John Mura, told Reuters, as these data centers get bigger and consume more energy, the grid is not designed to withstand the loss of 1,500 megawatt data centers without cascading effects. The technical reality is stark. A single AI-optimized hyperscale facility draws more instantaneous power than entire cities. When these facilities disconnect from the grid, whether for maintenance, emergency, or equipment failure, they create immediate supply-demand imbalances that propagate across regional transmission networks. The August Virginia incident demonstrated this propagation risk in real time. When 60 data centers simultaneously switched to backup generators, they didn't just remove their own electrical load from the grid. They triggered automatic protective systems across the Mid-Atlantic that nearly caused controlled blackouts from Maryland to North Carolina. Grid operators had minutes, not hours, to rebalance generation capacity across a 7-state region. Wall Street Journal analysis reveals that business investment in AI might have accounted for as much as half of the growth in gross domestic product in the first 6 months of 2024. This isn't sustainable economic growth. It's a financial structure dependent on continuous physical infrastructure expansion that is hitting hard resource constraints. Sam Altman's November 2024 statement that OpenAI is too big to fail and would likely receive federal bailout funding reveals the sector's awareness of this infrastructure dependency. When the CEO of the world's most prominent AI company explicitly compares his business to systemically important banks, he is acknowledging that AI infrastructure has become critical national infrastructure that current electricity systems cannot reliably support. Morgan Stanley's infrastructure analysis identifies external financing requirements for roughly half of projected AI data center spending through 2028. Unlike previous tech bubbles driven by software valuations, AI infrastructure requires massive upfront capital for power generation, transmission lines, cooling systems, and physical facilities before any computational work begins. China's electrical grid operates under centralized planning that can rapidly redirect generation capacity for strategic AI projects. The Chinese government treats AI infrastructure as national security infrastructure, with grid reliability receiving priority allocation. America's deregulated electricity markets create the opposite dynamic. Data center operators can outbid all other users because electricity represents such a small percentage of their total project costs. This pricing power allows AI companies to effectively commandeer electrical infrastructure while socializing costs to other ratepayers. The competitive implications are stark. America is fighting with an electrical grid built for 20th century load patterns against an adversary with 21st century industrial planning. As data center electricity demand increases, grid reliability decreases, requiring additional investment in backup systems. These investments increase electricity costs for all consumers. Higher electricity costs don't reduce data center construction. Developers are price inelastic, but they do reduce economic activity in electricity-sensitive industries like manufacturing and chemical processing. Caltech researchers quantified the public health costs in their December 2024 study. U.S. data centers in 2030 could contribute to 1,300 deaths annually from increased electricity production, resulting in public health costs exceeding $20 billion. The financial arithmetic is unforgiving. Data centers generate economic value for their operators while infrastructure costs, public health costs, and economic displacement costs are socialized across the broader population. The grid reliability crisis isn't a future problem requiring future solutions. It's an immediate constraint on AI infrastructure expansion that's already affecting electricity pricing, grid stability, and resource allocation across the American economy. Data center developers understand these constraints. Meta's 30% budget cut to Reality Labs after $70 billion in losses signals that even tech giants with massive cash reserves are reassessing infrastructure-intensive AI investments. The gap between AI hype and infrastructure reality is closing faster than most market participants expected. For consumers, the cost transfer is accelerating. Utility rate increases approved in 2024 will appear in household electricity bills throughout 2025 and 2026. States with the heaviest data center concentrations, Virginia, Georgia, Texas, Illinois, will see the largest residential rate increases as infrastructure costs reach ratepayers through regulatory mechanisms. The investment implications are straightforward. Companies dependent on stable, low-cost electricity face margin compression as grid costs rise. Companies positioned to benefit from electrical infrastructure investment, utilities, power generation, transmission equipment manufacturers, face unprecedented demand but also unprecedented technical challenges. Regional economic development faces difficult trade-offs. Data centers generate high-paying jobs and substantial tax revenue, but they also increase electricity costs for existing businesses and residents. States competing for data center investment are effectively subsidizing AI companies by socializing their infrastructure costs while privatizing their profits. This infrastructure constraint pattern has historical precedents. The 1990s internet boom required massive fiber optic cable installation. The difference: fiber cables could be installed incrementally without affecting existing networks. Electrical grid infrastructure operates under different physics. Adding massive new loads affects all users immediately. The financial markets haven't fully priced these infrastructure constraints. AI company valuations assume unlimited electrical capacity at predictable costs. Neither assumption reflects current grid stress testing results. The resolution requires either dramatic AI efficiency improvements or massive public investment in electrical infrastructure. DeepSeek's recent 18x cost reductions suggest efficiency gains remain possible, but deployment requires years. Meanwhile, electrical infrastructure requires 5 to 10-year development cycles. guaranteeing continued grid stress and cost transfers to consumers. The autopsy is complete. The diagnosis is clear. America's electrical grid is breaking under AI infrastructure demands that were never planned into the system architecture. The costs are being transferred to consumers through regulatory mechanisms designed for gradual, distributed growth. And the competition with China is being fought with 20th century infrastructure against 21st century industrial planning. The pattern is mathematical. The outcome is predictable. The only question is whether policymakers and markets will recognize the infrastructure bottleneck before it becomes a systematic failure.